Hello everyone. Welcome to our senior design project, designing a FiberWeaver for the Extracorporeal blood oxygenator. We are Anil, Selin, and Ege. First, let me introduce you the concept. So on the left, you'll see the ECMO cycle, which fulfills the function of the lung during surgeries. In the middle, you see its main component, the oxygenator. Its mandrel is tightly winded with membrane fibers. The properties of these membrane fibers are shown on the left. We have two types, 3M and E2. We analyzed both of them and compared them with fishing line and sieving thread. And for that, we used the Leica microscope. The materials correlate in terms of their dimensions and properties.
Our goal in the project is designing a machine which finds fibers into mandrels with high reliability. And our scope is controlling the speed of the guide and the mandrel according to desired tension and angle. In this slide, you can see our CAD design and our final prototype. We have two axes, one which the module moves linearly, the other one just rotates. Both of the movements are powered by stepper motors. In the left picture, you can see our mechanical components mainly. Both of the axes are powered by NEMA 34 type stepper motors. Rotational motion transforms into linear motion by using ball screw and linear carriage. In the module, we use three bobbins. The middle one holds the source and is connected to rollers. Others are completely free to rotate. The guide at the tip of the module is 3D printed and its position to the mandrel is adjustable. You can see the electronical components in these pictures. Two motors are powered by two microstepper drivers, which pulse per rev value can be altered. 32 volts per driver are given into the system. The tension sensor is given 24 volts, and its output is 4 to 20 milliamp range. To transform current into readable value by Arduino, we use two different components. The tension sensor is connected to a load cell transmitter, which we can program and calibrate. The other component is a signal transducer, which transforms milliamp input to 0 to 5 volt output.
To continue with our modeling assumptions, tension depends on the angle, which depends on some factors such as distance between guide and mandrel S, winding length L, and mandrel velocity. So from the figure on the right, these parameters are adjusted to obtain a desired theta value. For the mathematical model, there are mainly three equations to obtain a tension and theta angle. First, alpha is the motor step angle, which is 1.8 degrees for our motors, and omega depends on the motor step angle, and delta t, which is the delay factor. Here, it shows that by adjusting the delay factor, the speed values change. From the literature review, we found a similar product of 3M has a tensile strength of 0.6 newtons. According to our mathematical model, the distance between the guide and unwind roller should be 3.15 and 12 centimeter winding length, which gives us 0.7 Newton and 57.5 degrees. In addition, the relation between the velocity of the unwind roller versus tension and angle theta are figured on the right graph. It can be concluded that as the velocity increases, tension increases, whereas angle theta decreases gradually. To explain our live tension control mechanism, the tension values are controlled by adjusting the mandrel speed by implementing a PID controller from Arduino's library. In our block diagram, we aim to control the mandrel speed by converting tension to speed value with our mathematical model. The figures on the right show the tension data and converted speed data. After all assumptions and modeling, here is our operation process. First animation is a top view that shows the rotational and translational motion. Second and third animations are from a closer perspective to see the mandrel and winding process in detail. Translational movement causes an angle which provides a symmetrical winding on the mandrel, and the tension sensor can be seen from the last animation.
And as the conclusion, we observed our mandrel using a transparent and laser-cut probe sheet. Thanks to our mathematical model, the operation precisely generates 60-degree windings with the fishing line. And last but not least, let's talk about some further developments. First, we are going to test system with E2 fibers, and we aim to have adjustable angles during operation and also detect mandrel diameter values accordingly. These were our references, and thank you for listening. And if you have any questions, we're happy to answer them in our breakout room.